Hello, welcome to Amay Kadam's channel. In this video, we'll see design of an amplifier for maximum gain at a given frequency using single stub matching section. Even one can design the amplifier using lumped element components, but in this lecture we'll see how to obtain the matching using single stub matching section. Stub is nothing but part of transmission line. Now the process goes like this. Since we have to design the amplifier at 4 GHz, we'll select the scattering parameters mentioned at 4 GHz. So these are the scattering parameters mentioned at 4 GHz. So first of all, we have to check the stability of the amplifier, and for that the well-known test is there, that is K delta test. If the K delta test is satisfied, then the transistor is unconditionally stable. Otherwise, we have to plot the stability circle, and then we have to select the gamma S and gamma L. So first I will be going for the K delta test, and I will be storing these S parameters as A, B, C and D. Ensure that your calculator is in complex and degree mode. So I will be storing this S11, that is 0.72 angle minus 116 in A. So shift RCL A. Later on 0.03 shift angle 57 B. .6 angle 76 in C, and 0.73 shift angle minus 54 in D. So first we'll check the K, we'll go for the K delta test. So delta is nothing but S11 into S22 minus S12 into S21. So that is nothing but basically a determinant of the scattering parameters. In this case, our formula will be A into D minus B into C. So we'll type this thing. So alpha A into D minus another bracket alpha B into alpha C. So that turns out to be, I will convert this into polar format, 0.4875 angle minus 162.28. Now I will store this delta in E as a variable E in our calculator. So shift store this thing in E. Okay. So the mod of delta is less than 1. Now we have to calculate K. So the formula for the K is 1 minus S11 square minus mod of S22 square plus mod of delta square divided by 2 mod of S12 S21. So we'll type this thing. It will be 1 minus mod of S11 is nothing but A square minus mod of D square plus, and this is nothing but our E. So mod of E square divided by 2 into mod of S12 into S21. So that is B and C, P into. So we'll calculate this one, and K turns out to be 1.1947. So now we have to check the condition. For this amplifier, mod of delta is less than 1, and K is greater than 1. Therefore, the given transistor is unconditionally stable. So since the transistor is unconditionally stable, no need to plot stability circles, as entire Smith chart is stable. So now we have to design for the maximum gain. So as you know that for maximum gain there should be a complex conjugate matching. So gamma S should be equal to gamma in star and gamma L is equal to gamma out star. But gamma in formula also involves gamma L and gamma out formula involves gamma S. So after simplification of this one, it results into this formula. So gamma S and gamma L can be selected in this manner, where this B1, C1, B2 and C2 are defined like this. So first we'll calculate these parameters B1, B2, C1 and C2, and then we'll calculate gamma S and gamma L, and then using Smith chart we'll proceed for the matching of gamma S and gamma L. So we'll calculating B1 first. Observe this thing, the S12 is not equal to 0, so I am not assuming unilateral case. It is a bilateral transistor, and if the transistor is bilateral and one has to design the amplifier for maximum gain, then you have to follow this procedure. Okay, so I will be calculating B1. So B1 will be 1 minus mod of A square, sorry, 1 plus, it should be 1 plus minus mod of D square minus, and I have stored delta in E, so minus mod of E square. So B1 turns out to be 0.74781. Now to calculate, I will calculate B2 first, because I have to change the sign of S22 from minus to plus and sign of S11 square from plus to minus. I will do this modification. So this has to be plus, whereas this has to be minus, and I will calculate B2. So it turns out to be 0.7768. Note that if you have stored these S parameters as ABCD, one can reduce the computational time. So now I will calculate C1. So C1 will be, this is nothing but A minus delta, so that is nothing but I will put on one bracket alpha E into conjugate of S22. So to get conjugate, observe this thing, to get this conjugate, what you have to do, shift 2 and then you have to select conjugate, and S22 is nothing but our D, so alpha D. Yeah, so another another bracket has to be completed. So this is equal to, and I will convert this into rectangular polar format, and it turns out to be 0.3704 angle minus 123.4. Similarly, one can calculate C2 as Here I have to change the formula. Oh, this has to be A has to be D, okay, rather I will type this thing. So alpha D minus bracket for E into 2 conjugate of S11 star is nothing but A, and convert it into polar format. Get answer as 0.385 and angle is minus 61.02. So we have calculated B1, B2, C1 and C2. Now one has to calculate gamma S and gamma L. Now be careful, in gamma S we have again these two possible options, either positive sign you have to consider or negative. So remember, the sign selection for gamma S depends upon B1 or value of B1, and the sign selection for the gamma L depends upon the value of B2. Now B1 is greater than 0, so the sign that has to be considered is negative. Again, B2 is greater than 0, so the sign for the gamma L that has to be considered is nothing but negative. In case if B1 turns out to be negative, then one will consider positive sign over here. Okay, so for this numerical, your formula will be gamma S is equal to B1 minus square root of B1 square minus 4 of mod of C1 square divided by 2C1. Now what I will do, I will store B1 and C1 as variable B and C over here, and I can simplify the thing. So henceforth I don't require S parameters. So I will remove that thing and will calculate B1 and C1 over here. So my B is 0.74781. So I am storing this as B, while C1 I will store as C. So it is C is 0.3704 angle minus 123.4, and that I am storing as C. Okay, so now I will implement this formula. So it is B, alpha B minus square root of B square minus 4 into mod of C square, and here you will have 2 into C. There is no mod over here, here there is a mod. So gamma S will be a complex number. So get the value as, and convert this into polar format. So it turns out to be 0.871 angle 123.4. So similarly one can calculate gamma L. I am not showing the calculation for the gamma L, just I will mention this thing. B2 is 0.7768 and C2 is this. So you can store this as B and C, and one can calculate the gamma L. So gamma L turns out to be 0.876 angle 61 degree. Okay, so we have calculated gamma S and gamma L. Now we'll proceed for the matching of gamma S using Smith chart. So we'll write over here gamma S is equal to 0.871 angle 123.4 degree. So we'll proceed for the matching of this gamma S, and later on I will proceed for the matching of gamma L using another Smith chart. So gamma L is equal to 0.876 angle 61 degree. So now we'll see the matching of this gamma S. Now see the procedure. We are going to use the stubs in parallel. So it is preferable to convert Z into Y. So how to match this thing? So first we have to mark 123 degree over here. So from the center of the Smith chart, here it is 90, 100 and so on up to 120. Between 120 and 130 there are 4 minor lines making 5 subdivisions. So each subdivision will be of 2 degree. So I have to mark 123 degree. So the line will pass through from the center between the second and the third division. So 123 degree and 0.871 I have to mark. So I will go over here and I will measure the scale. So 0.871, 0.87, and I have marked this thing. So this is nothing but gamma S. But as we have decided to connect the stubs in parallel, we have to convert gamma S, which is equivalent of ZS, into YS. So one can obtain the admittance from the impedance by transforming this diametrically opposite on the Smith chart. So I will extend this line, and the same thing I will mark over here. So this point is nothing but YS. Okay. So to this I will draw a constant VSWR circle till it intersects the unity circle. So there are 2 points where this constant VSWR circle is intersecting the unity circle. So I will proceed for the design using the upper point. One can even design the stub matching section using the lower point. Okay, we'll see both the designs one by one. So I will read this wavelength scale over here using outer wavelength scale. So it is around 0.329 lambda. You may get some different value, but near about this one you will get. Now this is the point of intersection of the constant VSWR circle and the unity circle. So extend this thing on the wavelength scale, and this turns out to be 0.20245. So one has to travel the distance from YS to Y1 over here in anti-clockwise manner, because we are moving towards load. Though this is a gamma S, this point is gamma S, we always move towards the load. As just I will explain this concept. Okay, you will have design, you will have an amplifier, final amplifier design like this. Now here it is gamma S, and this is 50 ohm. This 50 ohm acts as a load for gamma S. Here it is gamma L. This 50 ohm acts as a load for this gamma L. Now when one has to match this gamma S with this 50 ohm, so this acts as a load, so we are moving towards load only. Though in diagram it is seen that we are moving towards source, no, but it is the source resistance, this is the load resistance, so it is we are moving towards load. So wavelength towards load, that means you are moving in anti-clockwise direction. So we'll subtract this thing and we'll calculate the distance of this stub. So it is 0.329 minus 0.205 lambda. So it turns out to be 0.124 lambda. Now we'll calculate the length of this stub. So you have to take this point along the arc. The given point may be on one of the printed arc or maybe in between two printed arcs. So one has to interpolate this thing and you have to go over here and then you have to measure the length. So mark the length. So it turns out to be 0.200 lambda. Now we are designing open circuited stub in Y. So as you know, this point is short circuited in Z. So this is short circuited point in Z. Similarly, the same point is nothing but open circuited in Y. So one has to always measure the length from this end up to this point. And this is nothing but the length of this stub. And length of this stub turns out to be 0.200 lambda. So if you consider this design, we have calculated the distance of the stub. Yeah, this distance of the stub as 0.124 lambda and the length of the stub as 0.200 lambda. If we select the lower point for the matching purpose, then one has to draw a line from the center of the Smith chart to this Y2 point and extend on the wavelength scale. In that case, the distance of the stub will get reduced, but the overall length of the stub will get increased. So depending upon the requirement, you can select the appropriate design. Now here again I will show the second possible design again for the matching of gamma S using the same Smith chart. So if I extend this thing, it turns out to be 0.295 lambda. So the distance of the stub will be 329 minus 0.295 lambda. So this is the distance of the stub, and now if you take this point on along the constant reactance arc, I will get the length of the stub as 0.300 lambda. So there are two possible designs for every value of gamma S or gamma L. One design you can consider by upper point of intersection of constant VSWR circle with unity circle, and another solution from the intersection of the VSWR circle with the lower point on the unity circle. So one will have D1 like this and L1 like this. One can have D2 like this and entire thing as L2.